Hi everyone. PreCalculus 1.2 Analyzing graphs of functions and relations. We are going to check zeros, roots, symmetry, even other function. Example 2. Use the graph of f to find the domain and range of the function. Okay, finding domain given graph. Domain is how far to the left to how far to the right. So graph, if you look at it, do you see this graph has arrow here? Meaning keeps going down, also keeps going to the left, keeps going to the left, left, left. So what's the most left you can go? Minus infinity. If you look at it, the graph stops right here. So most right you can go is 1, 2, 3. So minus infinity to 3, minus infinity to 3. Infinity, whether positive, negative, always parenthesis. If you look at 3, it's a solid dot. So you do bracket here. Interval notation or inequality. Inequality, x is less than or equal to 3. That's it. Range. Range means how low to how high. So if you look at the graph here, keeps going down. So how low, what's the lowest point the graph can reach? Forever to the downward. So minus infinity 2, what's the highest point graph can reach, which is 2. So minus infinity to 2, infinity always, whether it's a positive or negative, go with the parenthesis. If you look at the top, there's no hole. So it should be a bracket. Okay, so given this, use the graph of the function of g of x to approximate its y-intercept. Then find the y-intercept algebraically. Okay, graph is provided. How do you find the y-intercept? Just look for where the graph hits y-axis, -1. Then find algebraically y-intercept. So how do you find the y-intercept algebraically? Plug it in 0 for x, because every y-intercept has x value as 0. So that one, if you haven't forgotten, you do need to remember it. So plug it in x value as 0. So plug it in x value as 0. Okay, x value is 0 plus 2 absolute value -3. If you evaluate, it becomes -1. So that's algebraical way to calculate y-intercept. Okay, example 4. Find zeros. Zero is another way of saying x-intercept. Use the graph of f of x equal to x cubic minus x to approximate its zeros using graph. So if you look at it, here's a graph. Where does graph hit x-axis? Right here, right here, right here. -1, 0, 1. So those are the answers. Then find its zeros algebraically. So what if we don't give this, we don't provide this equation, the graph of the equation, and let's say you don't have graphing calculator. If I ask you find the zeros algebraically, so finding zero is the same as finding x-intercept. So how do you find x-intercept? Plug it in y as 0. Y, this is y, f of x is y. This is the same as this writing. So plug it in y as 0. You're solving for x. So if you have a cubic power, you're hoping to get the factor. So you can factor x out here. Factor x out, factor x out. With this x squared minus 1, you can interpret that as x squared minus 1 squared. And you can use the formula a squared minus b squared formula equal to A plus B parenthesis A minus B parenthesis. You do need to memorize this formula if you have forgotten. So using that formula, x plus 1, x minus 1, we factored. So after that, this times this times this equal to 0 means this is 0, parenthesis equal to 0, or this parenthesis equal to 0. So you let that each factor equal to 0. Solve for x. Here's a 0, minus 1, minus 1, plus 1, plus 1. So you got three answers, 0, minus 1, 1, which was exactly the same answer when we got the answer from the graph. Okay, so already have answers here, but you should be able to get all those answers given any graph. Find each of the following x-intercepts. So look at the graph. Where does the graph hit x-axis? Right here, right here. Minus 1 and 3. That's why we got minus 1 and 3. Okay. Y-intercept. Where does the graph hit y-axis? Right here, minus 2. Domain. What's the most left the graph can reach? Right here. 1, 2, 3, 4. Minus 4. What's the most right graph can reach? 1, 2, 3, 4, 5, 6. Minus 4 to 6. Minus 4 to 6. Solid dot, bracket, bracket. Range, lowest point graph can reach. Minus 4 here. What's the highest it can go? 1, 2, 3, 4, 5, 6. Minus 4 to 6. That's a mistake. It's minus 4 to 6 because it's a solid dot. Okay, so the answer is supposed to be minus 4 to 1, 2, 3, 4, 5, 6. 6 bracket, bracket. That should be the range. If one of this or both of them was arrow, if it was going up forever, then the minus 4 through infinity would be correct range. But not with this. If you're minus 4 to minus 6, bracket. Okay, where f of x equal to 4, where f of x equal to 4. What is f of x? Y. Y is equal to 4. Where's y equal to 4? 1, 2, 3, 4. Y equal to 4 is right here. When do we have y equal to 4? When x equal to minus 3, y equal to 4 is right here. Minus 3 for x and 5 for x. That's where y value is 4. So you got minus 3 and 5. F of 4. Okay, be careful. F of 4 means f of x. F of 4, f of x. What is 4? X value is 4. X value is 4. X value is right here. X value is 4. 1, 2, 3, 4. What's its y value? 2. Absolute maximum. Absolute maximum means the highest point on the graph, which you already know, which is 6. Absolute minimum, the lowest point. So it should be minus 4. Where is the graph increasing? So be careful when you trace this increasing, decreasing concept. You are tracing the graph from left to right. Left to right. What's increasing? What's decreasing? Y value. So as you trace to the right, I'm asking, is y value increasing, decreasing? Decreasing. So when we ask, where is the graph increasing? Increasing. We are asking y value is increasing. So as I said, is this increasing, decreasing? Y value as you move to the right? Decreasing. Y value is decreasing. From where to where? here to here, y value is decreasing as you move to the right. So interval from here to here is decreasing. One thing you have to be careful, y value is decreasing. When you write the answer, you need to write the answer from x value to x value. Where is it decreasing y value? Here to here. What's x value? -4. What's x value here? 2, 1. So the next question was, where is the graph decreasing? -4 to 1. Increasing, decreasing problem, always a parenthesis. Because at one point, it doesn't make any sense, increasing, decreasing. Increasing, decreasing is continuous motion. So at one point, we cannot discuss things about increasing or decreasing. So always use a parenthesis. So previous question, where the graph is increasing. Well, as you can guess, increasing starting from here to here, it's increasing. Where x value? 1, 2. X value here, 1, 2, 3, 4, 5, 6. 1 to 6, 1 through 6. So key point here is, you gotta trace graph to the right. If you trace graph to the left, you get everything wrong. Is a graph 1 to 1? Okay, 1 to 1 means passes a vertical line test, also passes a horizontal line test. It cannot pass more than once for any test. So vertical line test passes. Horizontal line test fails because right here it's passing more than 1 point. So it fails a horizontal line test. 1 to 1, no. Types of graphical symmetry. So if graph is provided, as you can see, it's a symmetric over x-axis. So we say x-axis is symmetry. If you look at this graph, it's a symmetric over y-axis. We say y-axis is symmetry. This kind of a graph, we call that as symmetric to origin, origin symmetry. What does that mean? This portion, this top right portion of the graph, you can flip it, you can reflect over y-axis, then reflect over x-axis. Then they're gonna match. That's what I mean by symmetry to origin. Okay, so it could be one of those symmetry, or it could be none of those symmetry. So some graph may not have any symmetry available. One thing you have to notice, recognizing symmetry given graph is fairly simple, as you can tell. There's more to it. When you try to show this symmetry algebraically, you need to notice this. X-axis symmetry, if you look at it, there gotta be matching points above x-axis, below x-axis. So the x values are same, the y values would be different sign. So it's like you got 3,2 here. You will have matching value 3, -2 here. So like that. So same x value will have different y value, so you can do symmetry over x-axis. So just that's one thing you have to keep in mind. If you're trying to show x-axis symmetry, what you can do is replace y with -y, and you have to show equation doesn't change. Because when you plug in y for -y, x value should be exactly the same. For same logic, y-axis symmetry, as you can see, any point on the right side of y value, there gotta be matching point on the other side of the y value. What does that mean? Y value is the same. X value will have different signs. If there's a +3 for x, there should be -3 for x for same value of the y. Okay, symmetric to the origin, x and y, you will have opposite sign for both. If you have x, you should have a -x. If you have a y, you should have a -y, which means there gotta be matching points with different sign for both x and y all the time. So this information, you do need to memorize it. And we will get to use this later problems. Okay, so here, use the graph of the equation to test the symmetry. Okay, given graph, it's very simple. You know, it's a symmetry over y-axis. So you say y-axis symmetry. This question did not ask, but it's also possible show algebraically the symmetry algebraically, which means this. So you figured it out, it's a y-axis symmetry, and you have to show algebraically how. Plug it in minus x instead of x into equation. Then show equation doesn't change. So algebraically, B-R-A, algebraically, you plug it in, start with the original equation, y-axis symmetry. What are you supposed to do? Plug it in minus x instead of x. Instead of x, you plug it in. Instead of x, you plug it in minus x. Okay, parenthesis, super important. So parenthesis minus a square, that becomes what? Just x squared plus 2. So when you plug it in minus x here, instead of x, you see there, this is exactly the same as original. So the equation did not change. So that's how you show algebraically. Okay. Use the graph of the equation xy equal to minus 6 to test for the symmetry. So this is the graph provided, so you can tell. So this top left corner of this graph, if you reflect over y-axis, you will have something like this. Then reflect that over x-axis, then it will match. So graphically, you know, this is symmetric over origin. Now, support the answer numerically. Support the answer numerically. Okay, numerically means for any point of the xy value, they're gonna be matching point with a different sign for both. So numerically here, xy equal to minus 6. Can you think of x value, y value which is satisfied is minus 6? You can choose x value as 3, y value as minus 2. So 3 times, if you plug in x value, plug in y value, 3 times minus 2 becomes minus 6, right? Numerically, since this graph is symmetric over origin, there gotta be another point with exactly same value with a different sign, minus 3 and 2, should be there. And all you have to do is show that, plug it in minus 3 here, minus 3 times 2, you do know that's minus 6. So given a point, change the sign for both x and y, that point should be on this graph. That's how you show numerically. Okay, algebraically, confirm algebraically is this part. Symmetric of origin, what are you supposed to do? Plug it in minus x for x, plug it in minus 4y, and the equation should not change. So original equation is what? X, y equal to minus 6. And I'm about to replace minus x and minus y. So replace x with minus x, replace y with minus y. As you can tell, minus times minus disappears, xy equal to minus 6. So original equation, after I substitute, exactly the same. That's how you show algebraically this function is symmetric over origin.